As more people turn to edge AI for powerful, decentralized solutions, the pressure is on to make sure these technologies aren't just fast and efficient, but they're also reliable in the field. In this episode, we're talking about something that often flies under the radar, but it could make or break your project, and that is the testing of electromagnetic compatibility, EMC, and electromagnetic interference, also known as EMI. So what are the common issues that pop up during testing? Why do some designs run into headaches with interference? And how can teams set themselves up for success from the start? For this episode, we're bringing in the big guns. Our experts presenting on the topic are Octavian Tudor-Stroh from Würth Elektronik and Thomas Maurer with Texas Instruments. They'll be sharing their firsthand experience along with a few stories from the trenches. So by the end of this conversation, you'll have a better sense of the practical steps and solutions you can apply in your own designs. You're listening to Würth Elektronik's What's Up podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists, who today are going to shine a light on how edge AI systems interact with their environment, especially when it comes to 10-base T1L with power over dataline transmission and sensor board design. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.
Okay, before we get started, let me first set the stage. So let me give you an introduction about this edge AI, which is like unlocking the real time at the edge. And there are a couple of tasks which are getting implemented. And one of them is the decentralized analysis. This is in principle to perform complex analysis directly at the sensor node. This means at the machinery itself. And one thing you want to do, because you do a lot of measurements at the sensor node, you want to implement data reduction, because a sensor can produce a lot of data. So reducing the data traffic is one important thing. And you're only, let's say, doing the calculation at the sensor node, and then you only sending the results towards the internet or towards a gateway which collects the information. By this, you can do real-time decision-making. For example, you can run some smart algorithms, some smart AI models in real time at the sensor. The benefit of those mechanisms is you reduce the latency and increase responsiveness because you do all the processing directly at the sensor or at the edge. You decrease the bandwidth usage and the energy consumption overall, and you also improve the accuracy and the relevance through the local processing at the sensor node. The key features here are in principle that you can integrate various sensor types. This is from imaging to audio to environmental. In our use case that we will show later on, we are basically measuring vibration. So it's also optimized for, let's say, low power computing in case you have some kind of battery power device. But I think low power is always getting very important. It's also a scalable solution, so you can deploy this on a large environment, and you can have a lot of data sets, and by reducing then the amount of, let's say, data, you just can combine this in the gateway. Also, because you will see later on that this is all IP-based, so Ethernet IP-based, you can reuse the robust security features which are there to basically protect your sensitive information. Okay, the application we are now looking at is predictive maintenance. And predictive maintenance is a topic where if you're not doing predictive maintenance, you can have unpredicted failure. And this could be costly because the tools and material can basically break. We have then safety concerns because when it breaks, it may hurt a person. And it affects production because if something suddenly breaks down in the factory, you have a production going on. You basically have like a production stop, which is not good to have. Therefore, there are different methods of maintenance, and besides the predictive, and let me just walk you through them. The first one is the corrective maintenance, which means when something breaks, you are sending a service person to this machinery and he fixes this. So this is like the worst case, because in this case you basically have like a production stop and you send someone to the machinery to fix it. Then there is preventive maintenance. This means you are sending a person on a regular basis to check the machinery, and if he sees an issue, he can, or if he sees an upcoming issue, he basically can repair it. So the chance to have an unpredicted failure goes lower. And the third item is the predictive maintenance. This is now you are detecting that an anomaly, that something comes up, and in this while the machinery is still operating, and in this case you are now sending someone to the machine to repair it before it basically breaks down. So I think this is the best case because you are avoiding a production stop. And what are the motivations to do this predictive maintenance? So overall, if it costs 50% more to repair if an asset fails and if the problem can be addressed before the failure happens. So we got this information out of an Amazon brief which I linked here below. If a machine breaks down, it's unsafe. So as I mentioned it previously, it can hurt someone. In worst case, someone dies. You can get fines. You can not pass an audit, and you have a production stop. And the last item is basically that you can also add predictive maintenance to an existing machine. So it's like retrofitting technologies. So you add this to your machinery in order to reduce downtime and increase availability and productivity. So let's look at this predictive maintenance in the example of condition monitoring. I think I mentioned this in the introduction. When you're doing condition monitoring, there are 3 items that you can measure. The first item is you can measure the current of a motor. The second item is the temperature, and the third item is this vibration. I think all of these 3 components, using all of these 3 components, you can identify if a machinery breaks. And now let's look, for example, at this vibration item. So first of all, the machinery works good, and at some point in time, there is a change in the condition, so which is shown here as the beginning of the damage. So it could be that some gear gets a small damage, and there's a first particle now in the system which is which can cause more damage basically. And here we have then this damage to an element. At some point in time, you hear then an oscillation. I often describe this as an analogy to a car, where when you drive your car, at some point in time, you hear like a noise which you think does not belong here. So the car still drives. However, it's maybe better to go to the mechanic so that he can check what's going on. Maybe it has too less oil or something like this, but however, it's better, basically you hear these noise, which should not be there. And this is basically going here to this noise development. At some point, the temperature will rise because there might be additional friction, and at some point in time, this motor breaks down completely. So, which is basically the shutdown of the system because of a damage of an element. This could be all related either to misalignment, to mechanical defects, to unbalance, and to loose fixtures. And for this, one of the methods is to measure the vibration. So attach a sensor to this motor to record the vibration on a constant base, and then share this result with a smart algorithm. So this is now an introduction of this demo system that we are now talking in this webinar. And it's a vibration monitoring with edge processing. And it's the data communication is done over the 10-base T1L with, so this is single pair Ethernet, 2-wire Ethernet with power over data line communication. So basically 2 wires, and then we power it via the same cable where we also transmit the data. So the system consists of a sensor over here. So you see here in this demo system, we can connect up to 4 sensors. We have then an analog front end, which is this device. And the analog front end is directly connected to the edge processing board, which is over here. So this is what you have at the machinery, and then you do the data communication and powering over the single pair Ethernet wire, and this can be up to 2 kilometers. And then we have a gateway board which collects the information and makes it available to the internet or to the cloud or to the operator, basically. The way how it works, we also show this at the bottom here. So we have on one hand the vibration sensor, then we have this IEPE board, which is the analog front end. So this contains of an analog front end and 4 ADCs. The ADC values are getting sampled by a processor that we have then on this edge processing node. Here we do now a calculation. In this example, we do an FFT calculation of the samples, and then we send this information. We could run more algorithms on this edge processing board, but right now we basically transmit the results of this FFT to the gateway board using over the single pair Ethernet. And on the gateway board, we then show this as in a visual representation. So you see here at the top, which is like a website running on the gateway board, where we show the spikes of the FFT, and then you in principle you run here like a mask over these spikes, and once the spikes crosses the mask, you can issue an alarm and inform the operator that something is now looking odd. Okay, let me then also introduce to you 2 more boards. I mean, not introduce, but because we just looked at them. So the first one is the sensor board. So this is for TI. In case you want to find more information, you basically enter this TIDA number, and this is the 010261 board. And on the TI web, you can find basically more information like schematics and the layout and the user guide of this board. So this board is using an AM24 processor. In this case, we are using a system on module from a third party from TQ System. This is in principle, we just use this method because we only need to produce the base board, which is the sensor board, and then we just solder on this SOM module. The board supports this the Ethernet PHY DP83TD510, and this is the 10-base T1L PHY. We also implemented a powered device for the power over data line. It can also do the power over data line serial communication classification protocol. This is this SCCP protocol. It's based on an MCU that we put there. And it can connect via this PHY interface that we shown here to the analog front end. It's typically powered then over the power line, but we also have the option to power it separately. As I mentioned, on the TI web page, you can find the reference schematics for this solution. Currently, this runs in FreeRTOS, and it connects to the gateway board, which I will show it to you in a second. Also, all the data communication, like the FFT calculation, as well as the interface to the ADC, is done by the R5F and by an IP block, which is called PRU ICSS. So the next board I want to give you a closer introduction is the gateway board. This is now, yeah, in principle, it supports 4 times single pair Ethernet, and you see these connectors over here. And we have the option either to use this, let's say this green block to screw on the 2 wires, or we have alternatively here like a connector. We also use here a system on module from TQ, and this runs now an AM64 processor from Texas Instruments. It's again the same motivation why we have used a system on module. The reason is we only needed to create the baseboard, and then we just solder on the system on module. Yeah, this system now supports a power sourcing equipment, the PSE, which means it will inject power and make it available to the sensor board. We also have implemented the SCCP communication. Here we are using an MSPM0 to handle all the 4 channels. We have then a cloud connection to which is like this normal Ethernet connection over 1 gigabit. The board is powered by 24 volt. We have the option for a USB 3 interface, and we have an option for a Wi-Fi and Bluetooth CC3301 booster pack. Also, if you go under this name, the TIDA 010262 at ti.com, and if you enter this in the search, you will find here also information about the reference schematic, the bill of material, the layout files, and so on. This now runs actually not in RTOS, but it runs in Linux. And we have implemented here an example which is based on Node-RED. So this is a very simple graphical programming language. To make the visualization, we run here an MQTT broker, which will collect information from the sensor board, and we also use Docker for the different cases. As I mentioned, this interfaces to the edge processing board, and we can actually interface it to 4 times the edge processing board. And yeah, that's basically it. Okay, before I go on, let's also spend a bit of time about this digital transmission over the 10-base T1L with the power over data line. So 10-base T1L is a very good way to send IP telegrams over a long-range data. So in our case, this system uses this method. So we can have a long distance in the factory floor to connect different sensors at various places in the machine. And as I mentioned, typically this is above 1 kilometer. You only need two pairs, so which is called signal twisted pair, and we combine the data and the power over the same wire. So no need to provide additional power to the sensor board. The advantages of this is that you are reducing cost in the infrastructure, so lower installation and cabling costs because copper is expensive, and you limit this to the single cable. You have increased flexibility, which means easy configuration and troubleshooting. Typically, when you are using 100 megabit or a gigabit, you have then 4 wires or 8 wires. So there's a lot of more, there could be more problems when you install such kind of systems. It has also an improved scalability, so you can easily integrate new devices or you can add new locations without extensive setup changes. In this demo that I introduced to you previously, we do the data processing now at the sensor node and only provide then the results towards the gateway board. So basically reduce the information that you need to transfer over the net. The monitoring function, which consists of anomaly detection and notification, can then be done on the gateway board, on the sensor board, and then only provide information when there is when some problems occur. Then we send an alarm to the gateway board, and the gateway board can then inform the operator of the plant to send someone for service.
All right, so thank you very much, Thomas. So now let's look at the basically EMC, EMI related products from our portfolio, which helped this design. So as part of the Würth Elektronik portfolio, basically we're able to support a wide range of applications with regards to EMC, but not necessarily just to EMC. In this case, we're talking about the EMC, but with a focus on industrial and automotive as well. So our components can cover a wide power range, usually from low power to high power filtering. So we have things like common mode chokes for the mains or for the low voltage and data lines, varistors, TVS diodes for surge and ESD protection, filter chokes, ferrite beads, XY caps, well, you name it, anything for interference suppression. But now let's focus on the industrial PoDL 10-base T1L design that we have been exploring so far, and look at the general block diagram, showing the most important parts of this application, and with a focus on the passive components. So this figure shows the general hardware topology of a PoDL system. On the left side is the PSC, the power sourcing equipment. So in this case, we're talking about the TIDA 010262. And on the right side is the PD, which is TIDA 010261. And then in between, of course, we have the transmission path. In this case, we have the cable. Now, this is an approximation of the system, and it's not a one-to-one TI reference design. And basically, it shows the interface connection with the primary transient protection, the common mode chokes, the transformers, and the secondary transient protection to the PHY. Okay, we can also see the coupling and decoupling networks of the CDN, which is formed by CMC2, the common mode choke 2, or common mode choke 5, depending on, if we're talking about the PSC or the PD system. Now, power and data are coupled together at the interface through the power coupling and decoupling network. The phi is AC coupled by the data transformer, T1, in both cases, T1 and T2. We have common mode choke 1, which basically is used to attenuate any common mode noise which is coming either from the data line to the phi, or if anything, there's any kind of noise in the phi area, it also helps to filter the noise going out from the phi. Now, the power sourcing equipment, the DC power of the power sourcing equipment is coupled onto the differential data lines and then decoupled by CMC2. Okay. Now, you might see this is a common mode choke, but you have the two dots and you might think, okay, this might be a weird connection. Well, this common mode choke is wired in this way because it prevents any kind of differential DC current from saturating the choke, so that the signal that opposes the impedance of each choke winding is thus decoupled. Sometimes, we have additional differential mode filtering, which we can add here. For the DC power, and we use that with additional inductors that can be placed either before or after the common mode choke 2 or common mode choke 5. We are also able to provide a wide variety of inductors here for both the power sourcing equipment and the power device, power supply sections. So with a wide range of inductance or saturation current ranges, various magnetic materials which are either optimized for the low frequency or the high frequency switching. So we have a complete portfolio for any kind of application. Also, the magnetics, in this case, transformer 2, transformer 1, common mode choke 1, and common mode choke 2. They have to be selected in a way to meet the droop, the return loss, and the mode conversion, which are specified according to the IEEE 802.3 CG standard. So you cannot just choose any kind of transformer or any kind of common mode choke that you might think is going to work. Those have to be basically tested and approved to be used in such systems. We also have transient protection at the input of the interface, thus at the primary side of the transformers T1 and T2. And we have a ground reference, which usually is the housing or the earth ground, depends. And for the transient protection at the secondary side of the transformers, we have a separate ground this time, as you can see, ground secondary. And this is the ground of the phi, and any protection devices for the phi are referenced to this ground. Now, let's move forward. We talked about, this term EMC, but first of all, what actually is EMC? So sometimes we hear EMC and EMI as interchangeable terms, but this is wrong because the concept of EMC, or electromagnetic compatibility, basically is the ability of a product or electrical equipment or system to function acceptably in their electromagnetic environment by either having limited interference on the other devices and also being able to function properly when exposed to electromagnetic interference. So electromagnetic interference is the amount of electromagnetic energy generated by my device, and electromagnetic susceptibility, EMS, is how well this device can function when it's in the presence of unwanted electromagnetic interference. Then, of course, we branch out and we have conducted and radiated interference that we test in the EMI. And for the EMS, for the susceptibility section, we also have conducted and radiated susceptibility, but we perform also some additional tests like electrostatic discharge, fast transients, and bursts. Now, if we were to visualize this EMC on a system level, we can see, various ways the noise can propagate from a noisy source to a victim and how it can couple. The electromagnetic noise could be coming from the mains grid in the form of conducted, either as differential mode or common mode noise, and basically coupled to other systems which are connected to the same grid. Or there's a different way it can be generated locally by a noisy source in the form of, again, conducted or radiated noise. The coupling method from the noisy product to the quiet victim can be, either in the form of differential mode or common mode noise, again, conducted through the mains cable or the common ground. In this case, usually is the earth ground or the reference ground. Or it could be noise that is radiated through the cables, radiated through the chassis. There's some openings in the chassis, and depending on the size of the opening, on the frequency of the interference, all of this noise can escape, okay? Now, there are four main coupling methods that exist in such systems or, subsystems. We have field coupling, which is magnetic and electric fields. If we're talking about, of course, in the near field, in the far field, you have the EM, so both the magnetic and electric field. We have inductive coupling from high currents. We have high di over dt. We have capacitive coupling, which is usually done because of the high dV/dt, so any kind of switching nodes, for example. And we also have galvanic coupling, or also called common mode coupling, because it's coupling through any kind of, let's say, the common ground, which in this case would be the earth. So a clear understanding of this, each individual coupling mechanism is required in order to identify potential problems. And this is applicable either at the system level. So we're talking about, I don't know, just the PCB or a product or a sub-assembly. So it doesn't really matter about which we're talking. The theory applies the same. So we just need to understand how the system is actually working and interacting with other systems. So what standard was used in testing the 10BASE-T1L? Well, given the application target of this design, which is industrial power drive systems, the most relevant applicable standard is IEC 61800-3 with the latest update from 2022. And this specifies electromagnetic compatibility requirements for those adjustable speed power drive systems, and also for the machine tools, also applicable. Now, this standard refers back to IEC 61000-4, which is, a set of standards used to test system-level immunity. And many systems designs specify one or more of these tests listed within the IEC 61000-4-X specification to comply with for reliability and, basically for reliability for the end customers. Also, there are like 3 different performance or acceptance criterion levels for each individual test. So we have A, B, and C. One important fact to state is that the definition of criterion A is very much, I would say, customer dependent, because for communication, of course, communication interfaces, usually often the less 3 consecutive errors are still considered criterion A, even though it specifically mentioned no loss or of function or performance even during the testing. Up to 3 consecutive errors are still part of criterion A. Usually the customer typically tests this, twice to the standard voltages specified in the standard. And what is very important, achieving criterion A, especially with any kind of EFT testing, is a very competitive advantage. So if somebody can do this test and they will pass the test, they will definitely have a competitive advantage, because it yields to a more robust system with better performance and usually less downtime in those harsh industrial environments. So we are able to support IC houses, but not just IC houses, also customers. But we are able to support the IC house application engineers with tests for their reference designs or evaluation boards, and as I was mentioning, customers as well, but only for pre-compliance measurements, just to check how the design or product is performing. And then, of course, we support also with identifying the source of the issue, and then we support with checking what optimizations can be done to improve those before the customer or the engineer actually goes to a full compliance test house. So we are currently able to carry out EMC measurements in 2 different locations, in Waldenburg, which is the headquarter, and also in Freiheim, Munich. And we are able to do both conducted and radiated emissions and immunity, usually in the power range of up to 22 kilowatts. But this, it's depending on the location. Okay. Now, we talked about the evaluation board, the reference design. So let's look at TIDA 010261. So this is the reference design, and we supported with checking the EMC performance. So we did the tests in our labs. We also supported the engineer with the debugging process and optimization process. So the EMC performance was tested against CISPR 32 Class B. Class B, this is because it's industrial class limits, where if we're talking about Class A, that would be residential limits, and they're even more stringent. But this board is to be used in industrial, so we went for Class B, CISPR 32. The setup is pretty straightforward. So basically, we need to have the board actively sending some data and communicating as it would do in real life. So what we did is we took 2 of these reference designs and we connected to each other to communicate between themselves, okay? Just to establish the communication. This is what you're looking at from 30 megahertz to 3 gigahertz in the picture is the EMI spectrum that we are getting when the full board is powered up. As you can see in the schematic on the right side, you know, the full board, we had an external power supply from the lab being used to feed the reference design. Everything was powered up and working, you know, the boards were communicating. And as you can see, it's very noisy. We have a lot of peaks which are above the limit. So, you know, we are definitely failing this test. But you might ask yourself, okay, it's failing. How do we debug it? Because it's such a complex system. We have communication, we have different power supplies, subsections of the power supplies. We have so many components on the board. How do we start? Okay. Now, we have the ideal diodes. We identify that we have a couple of DC to DC converters, the Ethernet PHY, all of the interfaces, CPU, RAM, SD card, okay? The easiest way, let's check the power supply section. And in order to check the power supply section, basically, we have the high-speed communication. We have the Cortex MCU, Ethernet PHY, SD, and they contain the software. So let's disable them. By disabling the PHY and the SD card, we ensure that absolutely no communication or even no boot up. And we are left basically with just the power supply. So we can see, compared to the previous slide, that some peaks are gone, but we still have a lot of the peaks above the limits, and we have quite a lot of broadband noise. Now, because we disable the communication, this is the whole power supply chain, okay? So we have all the way from the input, all of the little DC to DC converters. Then we need to narrow down even further. How we do that? Now, let's bypass the ideal diodes, okay? And the first DC to DC converters. So what we done, we disabled the ideal diode, we disabled the main DC to DC converter, which was converted from 24 volts to 5 volts, and we injected our power supply right at the, let's say, subsections of the small DC to DC converters, okay? So we're feeding directly the 5 volts rail. And as you can see, let's check again the difference. So we disabled the ideal diode, we disabled the big DC to DC converter, and now this is the spectrum we are getting. So this makes quite a difference, you know? The small DC to DCs are very clean, even though they're operating at 1 megahertz and have rise times in the range of 1 to 2 nanoseconds. On the switch node, we can see it's quiet as a whistle. So now we identified, let's say, what makes most of the noise, okay? But the question is, we also disabled the communication, the PHY, the SD card, the processor and everything. So that's how much, you know, how would these digital parts contribute to the actual noise? Okay, so let's enable them back. So once we enable everything back, we can see, okay, we have some, you know, 2-3 peaks at 200, 250, 1 gigahertz. But this is depending on the polarization, because if you look closely on the spectrum, You can actually see there basically two graphs overlaid, okay? Because we have both vertical and horizontal polarization of the antenna in the EMC chamber. So also, let's check the datasheet. The AM6442 MCU outputs a clock with a rise time of around 1 nanosecond. Checking on the layout, we found out that the layout was not actually designed for this, and this huge, this very fast rise time was not accounted for when doing the layout. Also, some poor ground plane use around the SD card, and also on the SD card there was no series termination resistors, and this could cause this high frequency communication between the microcontroller and the SD card to radiate. Just so you get an idea of the different SD card types, so we have SDHC cards, which usually use a 25 megahertz clock during the initialization, and then they transition to 50 megahertz later on. We also have SDUHS cards, and usually they start with the same 25 megahertz clock during the initialization, and then the clock jumps up to 200 megahertz later. So maybe this is some of the peaks that we are seeing. So what we did next, we identified this problem with missing the series termination resistors. We added the series termination resistors to the SD card. We used a slower SD card, and now the test is passing. Of course, we have still some peaks, but the peaks are below the limit. And of course, with the very small change in the lab, we were able basically to make this passable. So now, because the SD card section was fixed, let's go back to the power supply, which usually is the one causing most of the problems in any design. So we fixed the communication. Fine, we are passing the test, but yeah, we don't have our original power supply designed in, right? Let's enable the power supply. We enable the main 24 volts to 5 volts DC to DC buck converter, and we see there's actually, an increase in the spectrum. We have some broadband noise, but still the peaks are below the limit, which is good. So, but the power supply still needs some debugging. Now, and analyzing this DC to DC converter, it has a let's say built-in inductor, so it might be that there's any kind of switching happening, some hard switching, the high DVDT, then you get an electric field due to the high DVDT, and there is some capacitive coupling that it can happen, and then basically the noise from the DC to DC converter can couple back into the cables, because the cable connector, so the cable input for the power source, the cable connector was very, very close to this DC to DC converter. But still, we disabled the ideal diode, and we still get, of course, some broadband noise. But even this way, we can see that the noise is actually below the limits. So this kind of proves the fact that our ideal diode is one of the main culprits of the of our big spikes, and it's causing us to fail the test. And the debugging process in the EMC is very complex, especially if we're talking about such high speed and compact designs that have both the digital section and the power converters very close to each other. So a very good understanding of how the circuit works and good planning in debugging area, debugging area by area is necessary. So what I would say here for debugging this DC to DC converter, what would be the choice of action? Of course, we cannot do it in the lab, but the best thing would be to move this DC to DC converter further away from the cables. Now, it's very important to notice this test that we actually done together with the debugging and everything was actually more than a whole day in the EMI lab. So now imagine if you had to go for full compliance, directly for compliance for certification purposes. Well, if you would spend that much time in a dedicated lab for that, you would pay thousands of euros. And the best way to save on money is to, understand, plan, debug. You can go to a pre-compliance chamber like our chamber. You can sit down with our engineers, have a small chat, some debugging, and then you can prevent let's say costlier visits to a full compliant lab. Okay, now I'm going to hand over back to Thomas.
Thank you, Octavian, for this very good overview. I'm now summarizing here the solution and revisions to overcome these EMC problems. And I showed here a graphic of on the right side of the first prototype board. We call them this E1. And then we made, based on all those findings, we have done a revision, which is then E2. So this is like a hardware revision. So we basically addressed all this issue that we found and created an updated board. So the limitation that we have observed on the first sensor board, just to summarize this, is that we failed this CISPA 32, where the noise level were way above the limits. And there are 4 items that we identified. So one of them was this ideal diodes. So they can be a bit tricky because they have an internal charge pump, which can generate interference. And there was also a missing input capacitor, which amplified the issue. So this was addressed then in the E2 version. The second item is this SD card, so which operates up to a frequency of 200 megahertz. And because of these fast rise times of only 1 nanosecond, so here we matched the length and matched also the impedance to minimize the noise contaminations. Then we have used in power module, this TPSM 13630. So this was close to a connector. So we moved it away from a connector because it coupled noise into these power cables. And the last item is also that we disabled clock outputs of the PHYs. So typically the PHYs they have like a clock out in order to daisy chain multiple PHYs. And yeah, and it's also possible to disable this output in order to reduce unwanted interference. So the conclusion, let me summarize this. It's very important that at an early stage of the design, you do layout reviews to ensure optimal cost efficiency and that you avoid later on redesigns. Many times this is actually, you will have a redesign, but at least you want to make sure that you don't need to do like 2 or 3 or 4 redesigns in order to pass this. So tackling EMC from an early stage is very important. So you're focusing on providing component provisions in the schematic so you can do additional filtering when needed. Also, it's important to understand how each component, especially like the DC-DC converters, can influence the noise in a complex system. So a lot of this EMC and EMI issues can be avoided by taking care during the design and layout. So on one hand, you can stick to good layout and schematic recommendations, and many times the component data sheet, so the device data sheet, shows already good, good recommendations. So make sure that you read this in the layout recommendation part. We have also released on TR.com an application note about EMC and EMI compliant designs for single pair Ethernet. So if you are typing in this SNLA 434 in Google or at the ti.com webpage, you can find this. If you have later on access to this presentation, just click on the link. And also, I would say it does not hurt to add provisions like ferrite beads, TVS diodes, capacitors to your design as a safety measure. Later on, if you don't need them, you just unpopulate them. But it's always good to have a place, if you have a place to solder them on during the tests.
Thank you so much for tuning into this episode. Now, we know that while some streaming platforms are making the switch to video format, there are still plenty of listeners tuning in through audio only. So if you'd like to replay today's episode as a video or review any of the images, datasheets, app notes, or materials mentioned in this podcast, visit www.we-online.com/podcast. If you're ready to kick off your own design, you can download Texas Instruments reference designs right from the Würth Elektronik reference design page at www.we-online.com/icref. And once you've found that, if you need to order samples or request any quote, it is simple. Just get in touch with your regional Würth Elektronik contact, chat live with our online team, or place your order directly through the MyWE customer portal. You're listening to Würth Elektronik's What's Up podcast, where we're seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Würth Elektronik technical specialists. We're going to shine a light on interesting topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Würth Elektronik's What's Up podcast.